I've absolutely loved hearing about the stories that people have shared about Vera Rubin, so I'm very honored to be here. So today what I want to do is talk about using the wonderful data that we have from astrophysics and cosmology and the techniques that we have developed over time, and actually use it to comment on the particle nature of dark matter. So really complementing what we do in particle physics to what we do in cosmology. So I'm going to assume that most people are very familiar with this picture of the timeline of our universe. We start out very ionized and hot and dense, and eventually the universe cools off to form the cosmic microwave background by, through the process of recombination and creating neutral hydrogen. Now, called the dark ages, the universe is mostly neutral. And it's not until really this era called cosmic dawn, when the first stars form and they release a lot of radiation, that we have some observable signal. There is no observable signal. Okay, so some observable signal from this period of time in cosmological history, and then of course today we can observe galaxies. So there are these three, there's also Big Bang nucleosynthesis, but there are these three eras that I will try to discuss today. I'll mostly focus on the CMB. So there are a couple of ways that you can imagine taking CMB data and trying to extract information from it. The first is what Kobe Fierce has done, and that is to measure the blackbody spectrum of the CMB. So here we see the data points, and they very, very nicely match to a blackbody spectrum with a CMB temperature about 2.7 Kelvin. So you can also think about looking at the fluctuations on the sky away from this temperature, and that is the anisotropies that we heard about earlier. Here's the temperature and the polarization anisotropy maps. These are the latest from the Planck satellite that gives us the full sky observation of the CMB. So we can take these maps and cast them into a little bit different form. These are the temperature and the polarization power spectra as a function of the multipole moment, or if you prefer to think about the angular scale on the sky, the separation between 2 points on the sky. Okay. This is the data. These are the data points. The underlying gray curve shows the best fit theoretical model to lambda CDM, okay? And so in lambda CDM, we assume that dark matter is cold, it's collisionless, and it has to be about 6 times more abundant than baryons in order to reproduce these acoustic peaks that we observe in the CMB. Okay, so if we take seriously this idea that dark matter has to be some sort of matter component of the universe, right? It's going to have some properties like ordinary matter does. And so what are these properties of dark matter? It's going to be a particle. It has some mass. It has some interactions. And the typical story about how to think about dark matter has been looking for WIMPs, weakly interacting massive particles that we heard about earlier. And the WIMP scenario has motivated a lot of searches. Depending on how you read this Feynman-esque diagram, you get different search channels. So if you let time flow from top to bottom, you get 2 standard model particles, anything visible, coming in and producing dark matter. So that's the production of dark matter. The opposite direction is the annihilation of dark matter. So you can imagine trying to detect dark matter indirectly by actually detecting its annihilation products. And you can have direct detection events where we try to observe some standard model particle like a nucleon and interacting with a dark matter particle as we move in our galactic halo. Okay? So these are the standard searches that we do in particle physics, and our WIMP scenario is being a little bit stressed at the moment. So it's our initiative to go out and look for other things, look for other observables, ways that we can test this model, this this scenario. And instead of thinking about indirect detection and direct detection, I can think about what happens in the early universe that we can actually complement these indirect and direct detection experiments. And that's through the energy injection in the early universe of photons, of electrons, positrons from dark matter annihilation, and through the momentum that's transferred between the dark matter fluid and the baryon fluid in the early universe. Okay? So let's start with the annihilation of dark matter, or you can think about the decay of dark matter. The first thing I talked about was the blackbody spectrum of the CMB. And so if you inject energy, this is going to produce spectral distortions of the CMB. So in other words, it's going to move it away from just being a pure blackbody spectrum. And so here we're reading time starting early and going later from right to left. And so here, if you have energy injection, what you're going to do is essentially shift your blackbody. You're going to get a temperature shift. Okay, this is the photon energy on the x-axis versus the distortion signal that you would see. As the scattering between baryons and photons lessens and lessens over time, you get different sort of effects called mu distortions versus Y distortions. So while scattering is still efficient between the baryon and photon fluids, you're going to get something called mu distortions if you inject energy. And then as recombination happens, you get what are called Y distortions. Okay? So this is how you can observe this effect of energy injection in the early universe. And notice that it's really times before recombination that this is going to be sensitive to. So after recombination, we can look at instead the anisotropies and how the anisotropies are affected through energy injection post-recombination. So after recombination, here our black line is lambda CDM showing the ionization fraction versus redshift. And if you inject energy after recombination, you're essentially increasing the optical depth of the photon to less. You end up having a larger residual ionization fraction than you would have normally had just under lambda CDM. Okay, so you get a higher ionization fraction, or in terms of the baryon temperature, you are allowed to stay coupled, the baryons are allowed to stay coupled to the radiation longer because there are just more target scatterers to occur to keep the baryons thermalized with radiation. Okay, so the effect on the CMB is, if I turn the annihilation cross-section up very, very high, is this suppression of power more or less on all scales. Okay, so we can ask the question, given a cross-section, the annihilation cross-section that I'm going to input into my model, or some some dark matter decay, what is the data that fits this line very well? How much can I stress that scenario and still be consistent more or less with this line to, say, the 95% confidence level? So Planck has done this. Here is, for instance, for S-wave annihilation. This is in terms of the dark matter mass versus the annihilation cross-section, and everything above this line is excluded by Planck for various different annihilation channels. But this is nice because now we can ask in indirect detection experiments that we perform, what is the consistency between some anomaly that has occurred, say like with the AMS positron fraction excess, and a dark matter interpretation of that. Does that coincide, or does that, is that okay with the CMB constraints? And for this, the answer is that they are inconsistent with one another. You can do the same thing for dark matter decay. So here's the dark matter mass versus the lifetime. And for a bunch of different annihilation channels, you get different constraints on the lifetime. Another thing, let me pick a different paper, pick a specific dark matter mass, and allow the amount of dark matter that is decaying to change. And why I want to show this particular plot is for long lifetimes here, you see constraints from Planck. and over here are the constraints from spectral distortions. So really there's complementary information here between the different types of observations of the CMB that you can do that is really covering a lot of parameter space. So having both of these pieces of information is very important, okay? Certainly there is a lot of work that has been done on it. There are people in this room who I have not cited here, and I apologize for that, but this has been vastly looked at. One of the interesting things is that annihilation impacts the anisotropies mostly at a redshift of around 600. For decays, it's more like 300, but there's a specific redshift at which you can say in cosmological history, your annihilations or decays are going to have the most impact on your CMB spectra, okay? So I'm not going to talk anymore about spectral distortions. It turns out that for the case of scattering, the CMB anisotropies are going to just do better in general. So I'm going to talk about now this scenario of dark matter scattering, particularly with baryons, nucleons. So in the early universe, we have a bunch of protons. We have ionized helium. So this is what I'm talking about when I say standard model particles, okay? So let me give a very heuristic picture of what's happening in the early universe. The idea of acoustic oscillations is that, say, if you have a dark matter potential well here, and a dark matter clump over here making a potential well, you have baryons that see this well and want to infall into the well. Of course, pre-recombination, there's a bunch of radiation as well, so that radiation is going to create a pressure and want to push them out. So this system can have, be on lots of different scales with lots of different frequencies, and what you end up is a system of harmonic oscillators where you just get this infall and pushing back out of the baryons in and out of this potential well. So this is the Fourier space description of what's happening at early times, and the process of recombination cuts this off at a particular time. And that's when we see the CMB. So the question is, how does this scenario change when dark matter is allowed to have any sort of non-gravitational interactions, particularly with baryons? And the answer in general is small-scale suppression. So here we're now imagining putting actual particles, right, to create our dark matter potential wells. And if a baryon comes in and hits one of these dark matter particles as it's infalling, it can kick out one of the dark matter particles. So here, you can imagine this happening over and over again, and you can destroy very, very weakly bound structures. So any sort of very small potential wells that had very few dark matter particles in them, you can hit them over and over again, and that will completely wash out this structure, okay? So this is the effect that we're looking for in terms of what's happening with anisotropies. It's this blue line here, and you can see at low multipoles or at large angles, there's not that much suppression, and then it just gets worse as you go to smaller and smaller scales. Okay, so these two scenarios are very distinct from one another, and so it's possible to very easily disentangle these two effects from each other in the CMB. Okay. So now we can do the exact same game. We can say how much scattering can you have before you've stressed the data enough such that you've created an inconsistency. The difference between annihilation and scattering here is that annihilation, this power is suppressed on a lot of different scales, on all scales. With scattering, there's more suppression out here. So depending on where Planck data are the tightest, they're not very tight out here, they're very good over here. You have a lot of flexibility out in this small scale region. Okay, so there's a little bit of interplay here with different scales. So let me just show you what the momentum transfer rate, because that's what's important in the CMB, for the anisotropies divided by the expansion rate of the universe looks like as a function of redshift. So at this line of 1, if you are above this line, it means you have an efficient amount of scattering, and if you are below it, it means that Hubble expansion is winning. okay? I'm using a cross-section. I'm assuming that my cross-section goes like some constant times some power of relative velocity between my two scattering particles, okay? So this is a very generic sort of model. You can take lots of particle physics models and reduce the cross-section to this simple form. So for positive powers of velocity, you get this behavior. And this is setting this constant at what I find to be its 95% confidence upper limit. So for positive or non-negative powers of velocity, you get a lot of scattering at early times and less so at late times. Okay, so the dark matter and the baryon photon fluid are tightly coupled at early times. On the other hand, if you have negative powers of velocity, you have this behavior. And actually, for a v to the -4 interaction, you actually flip the slope of this line such that you have less interaction at early times and more so at late times. Okay, so these are two different classes of models that have to be treated very differently. Instead of showing you the momentum transfer rate, let me show you something that's a little bit more familiar in terms of particle physics. As a function of the dark matter mass versus the dark matter proton cross-section, for different models, everything above this line for a particular model, it's excluded by Planck data. Okay. These are for our non-negative powers of velocity. For our other velocity powers, this scenario gets a little bit more tricky. And the reason it gets tricky is because what do I mean when I say relative velocity for this sigma naught times v to the n, right? What is this v? And for the most part, we're thinking about the thermal velocity, okay? Just the thermal dispersion of the particles, so it's the temperature over the mass of the baryons and the temperature over the mass of the dark matter, right? When, as the universe cools, of course, these temperatures drop, and this relative velocity gets very small. Or sorry, this thermal velocity gets very small. But that doesn't mean that the cross-section is going to blow up, right? If you have a v to the -4, that's bad news. But that's not the only velocity at play here. There's also the baryon fluid versus the dark matter fluid, the overall motion of these two fluids that also comes into play. And when that happens, there's a lot of technical details that makes my life really difficult, and you get something that just looks very, very different. So here's what you get. This is the dark matter cross-section against the mass for v to the -4. This is the constraint that you get. So it's very, very flat until you get to higher masses. And if you were to completely neglect everything that I just said, this is the constraint that you would draw. So if you neglected this bulk velocity issue, you would be overconfident by over an order of magnitude. So this effect is very important and needs to be treated as such. So this is a story with the CMB, but of course we can ask, what does that imply for today's galaxies, right? I said there was this small-scale suppression, and that has an effect through other observables. So if you look at the matter power spectrum, so these are at the limits of the CMB that I found. This is the scale in inverse megaparsecs, and this is the matter power spectrum. And so you can see that there's a peel off from lambda CDM, and you get all these resonant effects because the dark matter is undergoing acoustic oscillations with the baryons. Okay. So this is at a scale of about 0.1 inverse megaparsec. So this is ruled out. So we can actually look and say, we have this small-scale suppression that we were able to test with the CMB, but this is going to have an effect on the galaxies that are able to form at later times. And so here's a simulation of lambda CDM. Here's a larger galaxy, larger dark matter halo, and a bunch of substructure that you see. And if you just put in a very generic small-scale suppression, you see that a lot of that structure goes away. Okay. So Risa did a very good job of explaining the picture and the simulations that go into this. If we look at, say, the SDSS identified dwarf galaxies along with the classic dwarfs, we can ask the question, what does it take to ensure that these objects still survive any sort of interaction that you give dark matter. Let me not dwell on other constraints except for one. So here is the direct detection constraint. So this is not drawn as normal. If you look at the scale of cross-section that we're talking about, these direct detection experiments are actually probing something well below what this plot is, right? So you see these contours that give limits at like 10 to the minus 44, 10 to the minus 46, right, centimeters squared. So I'm well above this, but at the same time, there's a what's called a direct detection ceiling, that if you have an interaction that's so high, then your particles, your dark matter particles, are not even going to be able to make it through the Earth to appear in these direct detection experiments. So they have a limited sensitivity at high cross sections, and so there's a ceiling associated with that. So here's the CMB constraint that I showed you from before, and this is the constraint if you consider the existence of the Milky Way satellites, and you can't wash out that structure, okay? So this is particularly interesting, I think, looking at direct detection versus what the CMB and Milky Way satellites can give you, right? If you were to ask, what does cosmology demand of dark matter? You'd say, well, it's a WIMP. It needs to, be completely non-interacting, et cetera, and that's what we search for way down here in direct detection. But if you really ask, what does the CMB truly allow? What does the data allow? You see near nuclear scale cross sections, right? Not quite there, but close. These are really strongly interacting particles. So I think it's interesting in the sense of what does cosmology actually tell us, and what are our assumptions based on the searches that we do on Earth. Okay. So I don't want to run too much over time because everybody's hungry, I'm hungry. I just want to point out that there's also an era of cosmic dawn. If you haven't heard, you should look it up. EDGES has claimed a detection of the cosmic dawn signal. I'm not going to go into it, but they see a much larger absorption of the brightness temperature for 21 centimeter than they should in the normal standard cosmology case. And the accompanying theory paper said, aha, a V to the minus 4 dark matter baryon scattering can get the job done. And so you can ask the question, does that align with other cosmological observables that we have, namely from the CMB? And if you were just to naively do things, you would need this cross-section to explain the EDGES result. And that looks perfectly fine. Notice that in the era that EDGES is making their measurements, the universe is mostly neutral, versus when I'm making I don't make the observations. When the CMB, when the CMB, we're talking about the relevant physics for the CMB, this is at much earlier times when the universe was completely ionized. So in terms of particle physics model, what gives you a V to the minus 4 interaction? And it's a Coulomb interaction. So if I were to take seriously the idea that this needs to be a Coulomb interaction, if dark matter has maybe a very small amount of electric charge, then suddenly this picture changes for what EDGES needs, because there are so little free ions during the time of cosmic dawn, okay? This is excluded, but yep, let me not do this. You can ask me about that later. So in summary, I just want to say that I think that these observables provide this really rich and unique way to go and search for dark matter particle physics in a way that is very complementary to what we're doing terrestrially or with like gamma ray satellites. And there are a bunch of things that I haven't even mentioned. So SPT and ACT are ground-based experiments, CMB experiments that can get out to much smaller scales. And they're ongoing and have upgrades and data from those upgrades that will hopefully come out soon. We have Simon's Observatory, CMBS4. PIXI is an experiment that could give us better measurements of the blackbody temperature of the CMB. for observations of our galaxies. I didn't talk about DES, and of course, the LSST, or the Vera Rubin Survey Telescope, hopefully, will be able to tell us a lot more information about dark matter at later times. So, thank you.